Hello, and welcome to my talk about approximately strategy-proof tournament rules in the probabilistic setting. This is joint work with Matt Weinberg. Since the title of this project is very long, let's break it down first by talking about tournaments. Let's suppose we're in the final round of a Swiss system chess tournament. There are exactly 3 players who have won all their previous rounds, so they're in the running for first place. 2 of them, let's call them A and B, are matched against each other in the last round, and the third, let's call her Kimberly, is going to win her game. Now, A and B are sitting next to Kimberly and her opponent, so they observe that she's going to win, and they also know that they're going to tie their game, which means that both of them will get a half point. That's no good, since then they'll end the tournament with 5.5 points, whereas Kimberly will have 6, so she'll get uncontested first place. So A and B, who happen to go to the same school, which means that they kind of know each other, talk to each other and arrange it so that one of them wins the game. In other words, they collude. Maybe A resigns, even though the position is totally drawn. Then at least B has a non-zero chance of winning the tournament on tiebreak. That's totally dishonest, by the way, but whose fault is it that things turned out this way? Is it the fault of A and B, or is it the fault of the Swiss system tournament, which set up this final round matching, incentivizing A and B to perform dishonestly? The reason why we study tournaments and tournament rules is to see if we can address some of these questions and possibly design a rule that minimizes the effect of collusion. The tournaments that we study are a little simpler than the chess tournament that I just mentioned. To begin with, there are no ties, only wins and losses. We also assume that the tournaments are round robin, so everyone plays everyone else. So an n-player tournament can be represented by a complete directed graph with n vertices. Each vertex represents a player, and an edge points from player I to player j if I beats j. A tournament rule takes in this graph and outputs a winner. For most rules, the winner is not deterministic. The rule chooses some player with a certain probability. This is pretty typical. For example, any rule that breaks ties randomly is random in some way. An exception occurs when a rule is Condorcet consistent and there exists a Condorcet winner, which is a player who beats every other player. In that case, a Condorcet consistent rule always declares that player to be the tournament winner. In this simple 4-person tournament with a Condorcet consistent rule, A would be declared the winner because they beat everyone else. This seems pretty obvious. Say, though, that D beats A instead. Suddenly, it's not as straightforward to determine who wins. A and D are tied for first place with 2 wins each, so you might assume the winner should be one of them. But maybe since D beat A, D should win? But since D lost to B, who only has 1 point, maybe A should win? Or maybe we should randomly choose between A and D. But how do we weight the choice? Do we give them each 1/2 probability of being declared the winner? Is that fair? Plus, you might even be able to make some sort of argument for why B or C should win. I mean, it would be kind of hard, but I guess you could do it or try. In larger tournaments with more players, the question becomes even more complicated. There are many ways to declare winners. Which rule is best? Well, maybe you want to choose a rule that minimizes the effect of tournament manipulation. In other words, you want to disincentivize cheating. So that is what we will be examining. Suppose a coalition of 2 players wants to manipulate a tournament such that, collectively, they have a greater chance of winning. We'll call this group of players S. They are able to change the tournament from what it might be originally, T, to an S-adjacent tournament T' by changing the result of the match that they play. So maybe one player throws a match to another. This is manipulation. We call a tournament rule 2 strongly non-manipulable, or 2 S&M, if a group of 2 players can't increase their collective probability of winning at all. As it turns out, you can't have a rule that's both Condorcet consistent and strongly non-manipulable, and we'll see an example of why shortly. So, we are forced to compromise. We prefer to keep Condorcet consistence over strong non-manipulability, since it seems natural that someone who beats everyone else should win the tournament. We define a rule as 2 S&M alpha if a group of 2 players can't increase their collective probability of winning by more than alpha. Previous work has shown that 1/3 is the lower bound on alpha. Consider this triangle tournament where everyone beats exactly one other player in a cycle like this. It's not automatically clear who should win, but any tournament rule must assign probabilities of winning to A, B, and C, and these probabilities must sum to 1. There has to be a winner. Assuming we have a Condorcet consistent rule R, then there exists some player, without loss of generality, let's say C, who wins with probability at least 1/3 under this rule in this cycle. So A and B have at most 2/3 chance of winning under R. But if A and B collude and A loses to B on purpose, then B wins with probability 1 because R is Condorcet consistent. So you see that arrow flipped and B is now pointing to A because B beats A. So A and B have increased their collective chances of winning by at least 1/3. That's why alpha is lower bounded at 1/3, and that's a simple example of manipulation. However, what if A and B want to collude, but they don't know the outcome of each match? And what if the outcome of each match is uniformly at random? That is, everyone beats everyone else with probability 1/2. And let's assume for now that if a cycle occurs, for example, if A beats B and B beats C and C beats A, then the rule we're using declares the winner uniformly at random. So in this case, A and B don't gain anything by throwing their match one way or another, since between the two of them, each is equally likely to be a Condorcet winner, and each is equally likely to be a cycle winner. So, okay, so we've concluded that if matches are uniformly at random like this, then collusion doesn't really help. But what if matches are almost uniformly at random? After all, in most tournaments, the colluding players do not know the outcome of every other match before they decide how to collude. That's really a best case scenario for the colluding players, so it's a worst case scenario for the rule designer who wants to minimize collusion. So let's take the other end of the extreme and consider a tournament where no one knows the outcome of any of the matches. To draw a real-world analogy, this is like examining the list of players before the start of the first round. You have some idea of who's going to beat who, but of course you're not sure. And let's assume that for some reason the colluding pair of players has to decide how they're going to collude right now, before they see the outcome of any matches. Of course, most real-world situations are probably going to fall somewhere in the middle. The colluding players are going to know the outcome of some matches, but not others, when they decide how they're going to throw their match. But that is a question for a different project. We define an n-player probabilistic tournament as a distribution over the set of all n-player tournaments. An easier way to think about it is a probability on the direction of each directed edge in the n-vertex graph that represents the tournament. I've included a diagram for convenience, and you see in this diagram A beats B with probability 1/2 plus epsilon, so it's not illustrated, but what you can conclude is that B beats A with probability 1/2 minus epsilon. So a probabilistic tournament is independent if all matches are independent of each other, and it's weakly epsilon bounded if probabilities are drawn from the range 1/2 minus epsilon, 1/2 plus epsilon. Of course, epsilon is at most 1/2. We want to know if we can construct tournament rules that have a certain probability of working here. Our main result consists of two rules that are 2 S&M 1/3 epsilon plus 2/3 epsilon squared, which is at most 1/3. And in fact, this bound is tight. Also, in the paper, we develop a useful way to analyze recursive tournament rules when applied to probabilistic tournaments. In fact, this analysis also works in the deterministic setting, since that's just a version of a probabilistic tournament where epsilon is 1/2. One of the two rules we examine is a new rule called randomized deathmatch, which is a tournament where, every round, only two randomly selected players participate in a match against each other, and the loser gets eliminated. The other is randomized single elimination bracket, which has previously been studied. RSEB randomly seeds a single elimination bracket with the tournament players, padding the original set of players with a set of dummy players to reach a power of 2 if necessary. The dummy players always lose, so they're the equivalent of taking a bye. Playing one is equal to taking a bye. It's just a little easier to think about. So this may not seem recursive at first, but consider the fact that randomly seeding a bracket with initial padding is equivalent to randomly selecting perfect matching with initial padding every round. Given that you win your first round in the single elimination tournament, you are equally likely to play any other first round winner in round 2. A third recursive tournament rule is randomized king of the hill, which has also previously been studied. Under this rule, every round, a randomly selected prince has to play everyone else, and everyone who loses a game gets eliminated, including the prince if they don't win all their games. But first, let's talk about the proof framework. Let's talk about the collusion itself and call the colluding players U and V, which we will call them from now on. At the start of the tournament, there is, of course, a non-zero chance that U and V are able to collude somehow, usually. Of course, U and V can only collude when they play each other, since that's the only match where they can control the outcome. If they never play each other, they can't collude, so their probability gain is 0. So every round something happens. Maybe we have a recursive event, which means U and V don't play each other, but they both remain in the tournament. So no collusion has occurred yet, but collusion might still occur, and we recurse usually to a smaller tournament because other players have been eliminated. Alternatively, if U and V do play each other, then one of them is eliminated and they can't ever collude again after that round. So we call this a terminal event because it terminates the possibility of collusion in the future. But this is a bad terminal event since U and V did have the opportunity to collude. So from the perspective of the rule designer, it would be ideal if this never happened. If U or V are eliminated by someone else, then they also can't ever collude. So this is also a terminal event, but it's a good one, which the rule designer prefers. Another type of good terminal event occurs if U and B become identically distributed. Then their collusion doesn't matter. What exactly does this mean? The simplest example is when U and V are the last two players remaining in the tournament. It doesn't matter then who throws the match to who, because obviously one of them is going to win, so the probability gained from collusion is 0. Another example is when they are not the last two players, but they both beat all remaining players with identical probabilities. Once again, if they ever play a match, it doesn't matter who wins or loses. They're not going to gain anything from throwing the match one way or the other. And I have included some illustrations for your convenience. We would like to bound the worst case scenario, that U and V meet and play a match, and that they are able to increase their collective chance of winning. The total expected probability gain from their collusion is the expected gain from the terminal events added to the expected gain from recursing to a smaller tournament after a recursive event. There's an inductive proof in the paper, and the main takeaway is that we get this expression that upper bounds the maximum probability gain that U and V can achieve, given that we are able to find these three values, C, B, and G. So we upper bound the gains from the bad terminal event, we upper bound the probability of a bad terminal event occurring, and we lower bound the probability of a good terminal event. So this is what we want to do when we reason about worst case scenarios, because we want to upper bound the effect of bad events and lower bound the effect of good events, essentially. So as a warm-up, we'll use the recursive framework to reason about some tournament rules in their deterministic setting when epsilon is 1/2 and all probabilities are either 0 or 1. So first, let's talk about this new rule, randomized deathmatch, which you'll recall consists of only two players playing a match every round, with the loser getting eliminated, and I've included an illustration for your convenience. It's clear that for this rule, and in fact for any tournament rule, the most win probability that any coalition can gain via collusion is 1, so C equals 1 is our upper bound. Next, we'll consider the probability of a bad terminal event, which occurs only when U and V play. If the tournament has n players, then there are n choose 2 equally likely matches each round, and the bad one is only one of them, so this gives us B equals 1 over n choose 2. Next, we'll try to lower bound the probability of a good terminal event. The general idea is that the only teams that are important to us are the ones that treat U and V differently. Suppose all teams either beat both U and V or lose to both U and V, then U and V would be identically distributed and collusion would have no impact. So we define LU to be the number of teams who beat U and not V, and LV to be the number of teams who beat V and not U. Without loss of generality, assume that LU is at least as great as LV, and I just realized that I've been saying teams here, we use teams and players interchangeably in the paper as well. As we just saw, if LU and LV are both 0, then there's no possibility of collusion, so technically the probability of a good terminal event is 1. If LU and LV sum to 2 or more, then the probability that either U or V plays someone who beats them is at least 2 over n choose 2. Finally, if LU is 1 and LV is 0, then we have exactly one team, call it W, that beats U but not V. There are still two matches that could be good terminal events. Either W plays U, then eliminates U, which is good, or V plays W and eliminates W, which means that U and V are now identically distributed. So these probabilities sum to 2 over n choose 2. So in all situations, the probability of a good terminal event is at least 2 over n choose 2, which means we can say that G equals 2 over n choose 2. And then given our values for C, B, and G, we conclude that the maximum gain from collusion is at most 1/3. Let's repeat the exercise with the previously studied rule randomized single elimination bracket. We note that once again C equals 1, and B, the probability that U or V play a match, is 1 over n prime minus 1, where n prime is the number of players after padding the tournament with dummy players. Recall that we do this so that the structure of the single elimination bracket is neat. And I've once again included an illustration for your convenience. And again, the calculations for G are a little more complicated. We define LU and LV as we did before, and point out that if they're both 0, we are already in a good terminal case. If LU is 2 or more, then U is eliminated with probability 2 over n prime minus 1. So that's already good. We don't have to worry about the rest. If LU is 1 and LV is 0, then the same thing occurs. Either let W be the unique team that beats U but not V, and then either U plays W and loses, or V plays W and wins. And these are both good terminal events again, so the probability is 2 over n prime minus 1. And then finally, let LU equal 1 and LV equal 1. And then let W be the unique team that beats U but not V, and let X be the unique team that beats V but not U. So a good terminal event would consist of U playing W or V playing X, but these events are not mutually exclusive, so they actually don't sum to 2 over n prime minus 1 as we want. But we then note that another good terminal event consists of U playing X and V playing W, since then both W and X will be eliminated in the same round, and U and V will become identical. So added together, these probabilities are 2 over n prime minus 1, and the full calculations are in the paper. So now we have G equals 2 over n prime minus 1, which works out nicely and shows that the maximum gain under RCB is at most 1/3, which is true and has been proven before separately using a separate method, which is very good news. So now we move from the warm-up to the general case, where epsilon can be anything. In our warm-up, we set C equals 1, which was trivial, but now we do not have that luxury, and we would like a tighter bound. We note that if U and V were to play, then regardless of who wins the match, the winner must beat the same group of other players in order to win the tournament. We call this group the gauntlet. For example, in a single elimination bracket, the gauntlet consists of all the winners of the other relevant matches, which are determined independently of the winner of the UV match. You can imagine that maybe all these matches have already been resolved, while the UV match is still going, so everyone's just waiting for U and V to finish up, and they'll all play the winner in time. Incidentally, this is where the proof fails for Randomized King of the Hill. You'll recall that in Randomized King of the Hill, one player is selected as prince each round. In that case, the gauntlet might change depending on who is prince, since U and V might beat different players with different probabilities. Anyway, the existence of the gauntlet means that the difference in win probabilities is at most 2 epsilon, because it's difference between 1/2 plus epsilon to some power, minus 1/2 minus epsilon to the same integer power. There's an additional factor of 1/2 plus epsilon because in an ordinary tournament without collusion, there's at least a 1/2 minus epsilon chance that the result of the UV match turns out the same way as the result under collusion. So we have to subtract that. Finding B, the upper bound probability of a bad terminal event, is a little more straightforward. In fact, it's identical to our calculations in the warm-up. The event itself doesn't actually change. Finding G is more complicated, and the full calculations are in the paper, but you'll see that it does end up the same as the warm-up, the results anyway, so these are what they are. And then, using our framework, we can conclude that the maximum gain from collusion caps out at 1/3 epsilon plus 2/3 epsilon squared for both rules. So next we want to know, is this bound tight? And the answer is, yeah, it is. Well, let's get into that. So let's look at this triangle tournament again. So this is familiar, but now it's a probabilistic triangle tournament. Everyone beats the person in front of them with probability 1/2 plus epsilon. So let R be any Condorcet consistent tournament rule. We don't know much about R, but we know that whenever a cycle occurs, R must assign win probabilities to each of the 3 players. There are 2 such cycles, which I've named cycle 1 and cycle 2, with cycle 1 being the more likely cycle. Let's call the win probabilities in cycle 1 alpha A, alpha B, alpha C, and the others beta A, beta B, beta C. We note that in a regular tournament, everyone's overall win probabilities look similar. There's a probability that that player is a Condorcet winner, and then there's a probability that either cycle occurs multiplied by their win probability for that cycle. So the only differences are in the values of alpha, beta, etc. They might be different. Now let's look at this version where A deliberately loses to B, so they're colluding again. Now this increases the chance of B being a Condorcet winner. It also increases the probability of cycle 2, and it means that cycle 1 can actually never occur. So we note that the overall probability gain in this expression, well, it exists, but it still has alpha and beta in it. But we do note that there are 3 possible coalitions here. So since the other 2 coalitions have similar probability gains, and by the other 2 I mean B and C and A and C, who do like their respective game throwing actions, you can just replace the beta and alpha terms in the AB probability gain expression to get the probability gain for those coalitions. And then if we sum up those probability gains and divide by 3, we get the average probability gain across all coalitions. And because the alpha and beta terms sum to 1 when all 3 of them together, we can actually just replace them with 1. So what happens is we get this average probability gain figure with only numbers and epsilon in it, and we get the same 1/3 epsilon plus 2/3 epsilon squared expression that we've always had. So because this is the average probability gain, there must be some coalition that can achieve at least this much probability gain, which means that no Condorcet consistent tournament rule can do better than 2 SNM 1/3 epsilon plus 2/3 epsilon squared, at least when the tournament is independent and probabilistic in this fashion. So in conclusion, we found a tight lower bound for an upper bound of probability gain via manipulation for Condorcet consistent tournament rules. We've also developed a useful recursive framework to help analyze recursive rules. Future work might find a way to reason about randomized king of the hill, which is more difficult to reason about because we can't easily compute the probability gain via manipulation due to its non-matching elimination rule. As we mentioned earlier, this messes up the gauntlet. Future work might also want to consider probabilistic tournaments that are not independent, so the matches might be correlated with each other in some way, their outcomes. The recursive framework could be used for other problems as well. Anyway, that concludes the talk. Thank you very much for listening, and I hope you have a good day.